back and redo what I just did briefly, and then bring us, just remind us where we are. So we're looking at inferences and inequality restrictions, and the restrictions are like right here, right? And so the key thing is it has some inequalities in it. Okay, and so it has this, you can't bootstrap that. And that's correct. It's just a regular bootstrap. Oh, the mic. Okay, yeah, that's better. Okay, so just to just briefly review, we have a linear IV setting, a model. You have these inequality restrictions that you would like to test, and we'll talk also about how to get a confidence interval by inverting the test statistic. And we just base the test on a two-step GMM estimator with optimal weighting matrix. There it is, right? There's the weighting matrix, some initial estimator of the parameters, GMM estimator, and then you get the optimal weighting matrix for ID with possibly heteroscedasticity. G hat of theta is the sample moments, and then you have the square root of n times the GMM objective function. So root n times the square root of G hat theta prime, omega hat inverse G hat theta. Okay, and then the restricted and unrestricted GMM estimators. This is the restricted one. Obviously, you minimize that objective function subject to both the quality and the inequality restrictions, and then the other one, you do an unrestricted minimization. There's no restrictions, and then the test statistic is the difference of these objective functions between the restricted and unrestricted estimator. Okay, all right. So, so now I'm just going to describe what we just did, how to construct a critical value using the bootstrap. So then you get this GI hat. Okay, what that is, all it is that's kind of a sample version of the true moments. Okay, and notice that what we've done here is we have and what we've done is we have normalized this. So actually it has sample moments of this thing are 0. So that enforces the moment conditions in your sample. Okay, the moment conditions have a sample average of 0, so that's enforcing the moment conditions. And then the bootstrap draw of these moments, we just interact as standard normal with these moment functions. And if you think about this, what's the distribution of this going to be? It's just going to be the same as the sample moments. So that's all this is doing, right? This thing is right. That's what all that's doing with the bootstrap draw is you're going to have a distribution of that. It's mean 0 because the sample mean of these is 0, and then actually it would be mean 0 anyway. So we're imposing the sample mean 0 though to make it work. And then, we take this root n, 1 over root n, times the sum of the standard normals times the GI hats, and that's called the multiplier bootstrap. Okay, and now the other thing that's done here, and this is done in other papers on inequality, testing inequality restrictions as well, we use a local version of the restricted parameter space. So this delta then, delta here, that thing is like approximately equal to root n. It's meant to represent root n theta hat minus theta naught. So locally, actually, sorry, no, root n theta minus theta naught. Okay, so that's meant to represent a local deviation away from theta naught of size root n. Okay. Okay, and then we have introduced the slackness parameter, and that makes more constraints bind as it increases. So if you set it equal to infinity, it makes all of the constraints bind, right? Because that makes the second term minus infinity, so the maximum of 0 minus infinity is 0. So then the constraints are here, right? And you have less than or equal to 0 for every single one of them. Okay, so a critical thing is going to be, as Nikhil mentioned, it's going to be, how do you choose Rn? So we'll get to that in just a second. Okay. So, so there's the local parameter space again. Okay, so this is the local parameter space. Okay, and G hat, that's going to be like our, that is in the sample we have, that's the derivative of the moment functions with respect to theta. Okay, that's a minus x, the sample average of xi times ei. Okay, and then these then are like these are the bootstrap versions of the moment functions. Okay, so you have this G hat of B, that's like G hat of theta naught. It literally has a property of mean 0 in the data that you have by virtue of the fact that we have normalized this to have sample mean 0. So that has mean 0, and then because the moments are linear in theta, G hat delta represents at order 1 over root n represents a deviation of theta from theta naught. So these are literally like the moment functions. These are the bootstrap version of the moment function. Okay, bootstrap version of the moments. You have theta. Okay, and so then for each bootstrap draw, we just recompute the test statistic exactly as we did, only we use this local parameter space here. Okay, and which poses the inequality restrictions with some slackness represented by R, and compares the restricted, there's the restricted objective function at 1 over square root of the usual GMM restricted objective function. There's a square root of the unrestricted objective function. Okay, and the root n has now passed inside. Each of these here has got an n multiplying it, right? Delta, remember, delta is approximately root n theta minus theta naught. So there's a root n there, and then there's another root n with G hat. Okay, and so that's how this represents. This actually is a bootstrap version of n G hat, the bootstrap version. N G hat. Sorry, theta prime theta G hat theta. Okay, square root of that. Okay, that's what each of those parts are, and then we're going to minimize over the restricted parameter space and compare that with the minimum over the unrestricted parameter space, and then look at the distribution of that. So it has nothing like a chi-square distribution because of the inequality restrictions. Okay, we're depending on the bootstrap producing the right distribution. What happens as you go to where the inequality restrictions are not or satisfied is the limiting distribution of this switches between the something a quadratic form and partly half normals. this was done a long time ago. That was figured out quite a while ago, what that looks like, that limiting distribution. The problem is it's discontinuity for the different cases. And the role of RN is to fix that. Okay. Okay, so the main assumption required for the test to be asymptotically valid is that theta naught is strongly identified. The critical value, depends on the slackness parameter. And as we mentioned before, the asymptotics requires that Rn converges to zero slower than the convergence rate of the restricted estimator. In this parametric case, that's 1/√n. And so if Rn goes to zero slower than the convergence to the restricted estimator, the convergence to the restricted estimator, the rate of that is 1/√n. Okay, so that's what I'm posed here. If this is non-parametric, in the paper, we do the non-parametric case, then it would have to be slower than the non-parametric rate for the restricted estimator. Okay. So right, sure. Actually, though, because Rn is going to zero, right? If you look at the, if we go back and look at the restricted parameter space up here at the top, Rn is going to zero. So in the limit, the restrictions that get imposed in this test, in this bootstrap critical value, are exactly the restrictions that are imposed in the data. I mean, the ones that get imposed in this bootstrap are exactly the ones that hold in the data, right? Because Rn going to zero, at zero, all you get, the only thing that shows up is this h of theta hat minus hj, which is whether the restrictions are satisfied in the data. When they're satisfied in the data, right at the boundary point, that's zero and the restrictions are imposed. And when it's not, when you're not at the boundary point, that's going to be going to, that thing is negative. So that's going to be blowing up actually at root n rate. And so that takes you away from the restrictions being satisfied. So actually, as Rn goes to zero, exactly the restrictions are imposed in this test statistic, which are true in the data, and so it's not conservative. Okay, so it's not conservative. Point-wise, the role of Rn is to take care of this uniformity problem as you move between when different restrictions are satisfied or not. And what happens is that it puts in enough local uniformity so the bootstrap works to give you the right answer. And that has some cost in terms of power. Okay, it turns out basically with these kind of inequality restrictions, it's impossible to get uniformity and the best power at the same time. Okay, so we haven't explored the whole possibilities of what you can do there, but it's impossible to do, and this at least gets you the uniformity that you need to get the bootstrap to work. Okay, right. So just that's a long way of talking about that last point. Yeah. Okay. So any questions about that? Yes.
So what happens when the parameter itself is estimated from moment inequality?
When it's what?
When the parameter itself is kind of estimated from moment inequality, so it's not point identified. It's
okay. So if it's not, so we're not working with moment inequalities. We're working with the genome objective function. But if it's partially identified and that objective function is not minimized uniquely at the truth, this still works. Okay, and so what you have to do in a partially identified setting is there's another slackness parameter. And for those of you, I don't know if you're going to see much about that here, but in a partially identified setting, when you estimate, you probably know this, right? When you estimate the identified set, you have to put some slackness into the objective function to get consistency, right? Because the argmax correspondence is not lower hemicontinuous, basically. So you put some slackness in for the objective function to get consistency. So there's an additional slackness parameter that shows up. So in the linear, that's the only additional parameter in the linear moment space that you need to, the only additional what do we call them, regularization parameter that you work out is that one. And we have conditions in the paper that allow you to do it. We actually, I'll do an example in a couple minutes about what happens when you do that. So great question. Yeah. So yeah, we're not explicitly doing moment inequalities. I should say that this idea, this kind of slackness parameter is built into some of the moment inequality estimates too. What's different is we're applying it to objects that hold exactly and without randomness in them. It's kind of, we're applying it to the constraints rather than to the moment inequalities. And you can't get the same thing by just putting in the constraints in the moment inequality, because the constraints hold exactly and the moment inequalities are random. And so it doesn't produce the same answer. So it's not quite the same thing. It's we're imposing it directly on the constraints. Just as so, like if you were doing, let's see, how's a good way to say this? You could do GMM, and if you have linear inequalities, you could add them as constraints. That's not as good as imposing that the constraints hold. It doesn't produce as an efficient estimator. Actually, it's inefficient. So just treating them as well, so if you invert the matrix, that puts infinite weight on those things. Anyway, it's okay, but if you did GMM with a weighting matrix, which is not the optimal one, and that's you're kind of treating them as random, and that's not the right way to do it. You impose the restrictions on the parameters, and then you minimize the objective function. Okay. And so that's the way we differ from the moment inequalities type thing that people have done with the slackness thing. Any other questions? That's a great question.
You mentioned previously that these do not have to be strongly identified. Is that different from the standard point identification talking about previously?
Everything we've done here is strongly identified. We haven't done the weak identified case. I don't think we see much about weak identification. Sweet, right? Yeah, we're looking for those identified parameters that are identified from the structural models. So, yeah, good question. Good question. Anything else? Yes.
Is there an approach for MLE?
Good question. No, not yet. We haven't done it for MLE. The question is, how do you get this conservative thing? And you see that imposing the constraints conservatively drives the GMM objective function out. Right. And why is that? Well, because you're minimizing. Yeah, why wouldn't it do the same thing for the MLE? I don't know. It should work. I would think it would work if you do it the right way, but we don't have theory for that in this paper. If Andres were here, he'd be able to give you a much better answer. I'm sure he's thought of it. Andres Santos is Victor Truzakov, and Andres Santos is a co-author, and Victor were here same thing. So, but I don't know off the top of my head. We haven't thought about it. And I know that I understand the logic of the conservativeness of this and getting uniformity that way for GMM. I really haven't thought about anything. Good question. Yeah. Good other questions. Okay. Yes.
How would you change the bootstrapping if you have generated regressors?
Oh, okay. Great question. Let's see. Yeah, you have generated regressors here. Yeah, so I'll give you the answer that kind of avoids the issue entirely. Is you take both the moment conditions from both steps and stack them up, right? And then you're fine. Can you actually do it on the second step? I think so. But I think that would work fine if you set up the bootstrap the right way. I'd have to think about how to do it though, because then how do you account for kind of the first step in this? I don't know whether you can do that. I don't have an obvious way to do it. It's a good question though, because a lot, that's where a lot of structural estimators are just two-step estimators. Okay. All right. So, so setting, talked about this, setting Rn equals infinity is theoretically valid, but it's conservative, in other words, you get a conservative test. But it results in a loss of power. So you want to choose Rn the right way. Heuristically, Rn represents sampling uncertainty and H of theta hat minus theta naught. You want Rn to go to 0 a little slower than the sampling uncertainty in that, right? So you want to set it to be kind of a large value potentially, right out above how fast that's going to 0. Unfortunately, we don't know how to make that work because the distribution of that is not, it's got this discontinuity in it. And so we don't know how to do that. So we suggest maybe setting Rn to represent the sampling uncertainty and the unrestricted estimator at the constraints. Okay, so the restricted estimator is hard to work with because of the non-uniformity. So we look at the unrestricted estimator. And you can choose it's straightforward actually to choose Rn so that the bootstrap analog, you have the, Rn is to the right by an amount which has probably 1 minus gamma n. And gamma n, the point of that is gamma n is more interpretable. It's more interpretable as a tail probability than Rn. In the simulations, and we don't know quite what to make of this, but it doesn't matter much, actually. Whether you set Rn equals infinity, or you set this to be gamma n to be 0.05 doesn't seem to matter. So we did simulations for instrumental variables subject to inequality restrictions, and didn't seem to matter much in that case. And maybe that's just a simple problem where, we don't have an answer on that yet. But anyway, you can do this. It's straightforward to do. This is a max of a bunch of normals that you can think about using simple Bonferroni bounds to figure out a gamma n, and we've done that. But it doesn't actually affect the results much. Okay. So that's a good thing, right? It's not that sensitive in any case to gamma n. Okay. Now for confidence intervals, okay, we'll look at a confidence interval for a linear combination. It's a little harder. What we just talked about is getting critical value for a test. It's a little harder. We're going to invert the test statistic. And that's in a more complicated model that you might get in structural estimation. That's a much more challenging thing to do, but has been done. There are 2 papers, 2 quite nice. We think they're quite nice. I think other people think they're quite nice papers that have done this. Structural papers published in Econometrica that have actually used this already to get to invert to get critical values in a couple of these papers. There's one by Torgovitsky, who is looking at partial identification of dynamic effects in panel data. Okay, and he used this approach to get critical values, and then a paper by Pat Klein and 2 other authors whose names I will provide later. I'll look it up. Who was looked at trying to see if there was discrimination in firm data, and underlying that they had some probabilities for possible preferences that They constrain the V away from zero, and they use this to get to get to confidence intervals for their parameters. Okay. So what you do is you think about a possible linear combination, find a set of F, so these are possible linear combinations, such that the test statistic is less than or equal to the critical value for a test of whether or not the linear combination is equal to that F. Straightforward to do, right, using what we did, but you have to do it multiple times, like on a grid of possible F values, and then you take the confidence interval to be those grid points which are, less than or equal to what you don't reject, right, using the test statistic. Okay, and the paper describes, okay, so that's how you get the confidence interval, and as I said, it's been done in some papers, and reportedly, it wasn't too hard to do. For not being very precise, but anyway. Okay, so now when you go to parse identified parameters, there's an additional tuning parameter for estimating the identified set. That's this upper bound on the objective function. And so there's an additional tuning parameter you have to worry about, and it makes it more complicated. And then when you have nonlinear moments, which is true in a lot of structural models, then it's more complicated still. And the issue there is the local parameter space. In here, oh, it's right here. At this local parameter space, you now have to it's now nonlinear, and so you have to linearize it and then put in another tuning parameter here, right, that controls the linearization. Okay, and so that's a pain, actually, and we don't have a really good working example of that, actually. So, okay, all right, so that's so that works. So I want to do actually any questions about this? Any questions? Yes.
What does a critical value represent in these kind of confidence intervals? Because it's not normal distributed.
Right. No, absolutely not. So it's not chi-squared, right? This, you think the difference of restricted and unrestricted GMM objective functions has to be chi-squared. It's not that. So it just represents a probability statement. So, right, you're saying, so that's inverting a test. You're kind of saying, you got something that gives you the correct probability. You have a test statistic that's a function of theta, and let's just do the simplest case here. I'll try and reproduce this. Is a stretch for me probably, but you have a test statistic, right? T hat of, and you want to say you reject the null, right? If this is greater than or equal to some critical value, right? And what you need is you need to be able to set that critical value so you know that probability, right? Well, what the test inversion does is that the confidence interval, the corresponding confidence interval, is the set of theta such that T hat of theta is less than or equal to C, right? And so that gives you the right probability, because what you want to say is that your confidence interval is such that it contains the true parameter, right, with some probability that approaches something. Well, the true parameter, okay, so let's see, right, you know that the probability that T hat of theta naught is less than or equal to C. So the set of all thetas is a possible true parameter, and that makes the confidence set valid. I can't do that off the top of my head. But that's the idea of inverting a test statistic. Okay. Great. Thanks. Another question? Okay, so the risk of being thrown out of the room, but because Everybody know who the editor of econometric is? Uh, This is not a structural empirical example, okay? It's a causal one. And not only that, but it's local average treatment effects. Okay, so we illustrate the preceding discussion. We looked at a study by Angus and Evans. Am I going to be kicked out of the room for doing this? Okay, and we use the Angus and Evans study. It's on the causal effect of childbearing on female labor force participation. Use the 1980 census public use microsample restricted to mothers aged 21 through 35. The outcome of interest is a binary variable indicating whether mother's employed. Treatment is a binary variable that indicating the mother has more than 2 children. The instrument is an indicator where the first 2 children are of the same sex, and the parameter of interest is the average treatment effect for compliers, the local average treatment effect. They document that the impact of childbearing on labor force participation depends on observable characteristics. And in particular, their 2-stage least first estimates suggest a negative impact of childbearing on labor force participation across different levels of schooling, with the magnitude of the impact decreasing with schooling. Okay. And this may reflect the fact that more educated mothers have a stronger attachment to the labor force. To examine this claim, we introduced dummy variables for each year of schooling between 9 and 16 and for categories of less than 9 and more than 16. And we test whether the local average treatment effect is increasing in schooling. Is an objection from a structural person? Okay, so both hypotheses fall within the framework of linear ID with inequality restrictions. Okay, weight is identified through linear moment restrictions, and the hypothesized restrictions are linear in the weights. And so we use 5,000 bootstrap replications. We set Rn equal to plus infinity, or Rn is determined by gamma n equals 0.05. Okay, and we test the null hypothesis that you have this monotonic relationship across years of schooling. And as let's see, as years of schooling go up, the effect of childbearing and labor force participation is monotonic. Okay, and so the p-value for late being non-decreasing is 0.21, so it's not rejected at conventional significance levels, and the p-value for late being non-decreasing and non-positive is 0.9394, so that's even less evidence against that. And what we have in the data is it's actually non-decreasing in the data. So you know, the estimated values are monotonic. So you know, I'll check. You can look at that and see. And so that's why you know, it's imposed. It shows up in the data, and so. I'm sorry, they're negative. The estimated values are all negative. And so imposing non-positivity, you know, all that does is make the test worse or makes the p-value go up. Okay. Okay, so here is the unrestricted estimates. Okay, and can I draw on this? I can. Okay, so that's the unrestricted estimates and the restricted estimates. Okay, so you can see it's non-monotonic, it's negative. Maybe not, actually. I thought they were all negative, but they're not. Some of them are positive. Okay, and then the restricted estimates have that monotonic form. And then what we give, the next one is the confidence interval imposing monotonicity. Okay, and the point of that is it shrinks the confidence interval quite a lot. Okay, so when you actually impose monotonicity on this, which we have not rejected with the test, you shrink the confidence interval quite a lot. And what it does is, in particular, at points where you have this fluctuation going on, it shrinks a lot. Okay, and then you can do the same thing with monotonicity and negativity, and that also shrinks them a little bit more, particularly in the upper tail. So that's what we just did. And now you can also look at trying to get, to look at a non-identified thing, you can look at the average treatment effect. Because the compliers, the proportion of compliers in the data is quite small, you don't get much power from doing this, okay? They're not, average treatment effects not well identified, and that's what the confidence interval looks like. Okay, it does shrink it some, right? There's the restricted estimates in the blue for the average treatment effect, and it does shrink it a little bit, but not much. And that's because the proportion of compliers in the data is quite small. Okay, any questions about that? That's testing, a way to test restrictions about parameters of interest and the GMM setting when you have and a way to get confidence intervals for limit parameters of interest that are functions of all the parameters when you have any quality restrictions being satisfied. For example, the restriction that probabilities are positive, not negative, right? That's an example of it. Okay. Any questions about that? Okay. So let's go on now to a method of simulated moments, okay, which is important in structural estimation. And so we'll talk about that, and then we'll do discrete choice models. Okay, so in some settings, the moment functions are actually integrals, right? And actually binary choice and multinomial choice is like that, and we'll talk about that. And what method of simulated moments is useful for is replacing the numerical integration to get the exact moments with simulation. Okay, so that's what this is going to be useful for. We're going to use simulation to avoid having to do this numerical integration. Avoid having to do this numerical integration, and we're going to use simulation to do that. Okay. Now, in order for this to work, this f of s has to be a known PDF. It's not known up to parameters. It has to be known, specified. And so what that means is all the known parameters are included in this K. All right, and particularly they're included in that theta. So in this notation, if you thought about, what you really wanted to integrate over was some Gaussian with mean mu and variance sigma squared, you have to include in K in this notation that mean parameter and the variance parameter. Okay. And so I'll give you an example of that for mixed logit. So you see how this happens, but that's the way this method of simulated moments works. Is there's some known distribution of S that determines this integral. Okay. So the computation of this can be very difficult, and one of the very best examples is multinomial choice that we'll talk about, and that's what this was. That was McFadden's motivation for developing this, and Ariel Pecos had like even much more general motivation, like these patent models. So there are lots of other examples too, in structural models where it's very difficult to do this integration. Okay. So that's the motivation for this. Okay. And one can replace these the true moments by an unbiased estimator obtained by a finite number of simulations without affecting consistency of GMM. As I mentioned, Ariel in the patents paper did this and applied it before the theory was really understood completely, and then McFadden developed this for discrete choice models, multinomial choice in particular. And he and Hicks and Pollard worked out nice theory having to do with this. And you'll see why the theory is useful in just a minute. Okay, so to describe the method of simulated moments, let S1 through Sm be M random variables independent of W with marginal P f of S. Okay, so you're just gonna, and think of these, you're just gonna draw them from whatever f of S is. You know, invert a CDF to do that, or you know, if it's normals, you know, there's easy software to draw normal. Okay, so we're just going to draw them from whatever f of S is, and we're going to draw m of them for each observation. So for each W, there are these S1 through Sm associated with W, and we'll consider like an augmented data observation. This is one way to do the notation. There's other ways. Wm consists of the original data plus these simulation draws. Okay, and the key thing here is that each of these simulation draws have exactly this distribution f of x. So the simulated moment function is just the average of this over the simulation draws. Oh, so one critical thing, right? Where is it? Independent of W. This is absolutely essential. They're independent of W. Okay, now you may, they're independent of W. You know, it's just this distribution of S doesn't depend on W. It's already written there. It does not depend on W, so you draw them independent of the data. Okay, so it's absolutely critical for this to work. And then the simulated moment function is just to take the sample average of these over the simulate, not the sample average, the average over the simulation draws of the K function. All right. Simulated GMM method of simulated moments is constructed then by just taking these simulated moment functions and averaging them over the augmented data. Okay, so you got your data, original data, and then you augment it with these simulation draws, and then you average the you know, the simulated moments over all the observations, including these simulation draws. Okay, so that leads to a moment vector, a sample moment vector, which looks like that. It's the average across the observations. Okay, I equals 1 to n of the average across the simulation observations for each I. Okay, so there's an SJI. Actually, it's an SM. Sorry about that. This J should be M. Okay, it's an average of K over those draws of the S. Okay, where you do that for each I. So for each I, you're going to draw M of these specific to the I. Okay, and then you're going to average across those M, and then you're going to average across all I's. A simulated GMM estimator, just, you know, GMM with this as the moment function. Okay, so that's the moment function. You just minimize the quadratic form. You know. It's consistent and asymptotically normal under the same assumptions as GMM, same specification, and a really nice and useful property is that the identification conditions for simulated GMM are identical to the identification conditions for the true moment function. Simulation doesn't affect identification in any way at all. Okay, and you can easily see that if you look at the expectation of these moment functions. You just take iterated expectations, look at the expectation conditional on the data. That's the expectation condition on the data of these, you know, the sample of the simulated average of these K functions. And because they're independent of W, that just becomes the integral over F of S of the K, and that's the moment function. So the expectation the simulated moment functions is exactly equal to the expectation of the true moment functions for every theta. So there's nothing lost in identification by doing simulation. The expectation of moment functions is the same. Okay, so that's good. Okay, and okay, so we have, one set of moment functions has population expectation. The simulated moment functions have population expectation 0, if and only if, right? The true moment functions have expectation 0. Okay, so there's nothing lost. I'm just going to leave it at that. Sorry. Yes.
So since S is independent of data, you actually need a different set of S for each observation, or you can use the same set of S?
I'm going to give you different.
Since S is independent of data, right, do you actually need to draw a different set of S for each I versus just using the same?
Yes, I know you don't need to for this property, but if you want to preserve the variance properties of the moment functions, you would do that. You would draw a different S for each observation, because that makes the observations independent of each other. So like in Ariel's case, in the patents paper, so it's just, you have the moments and then you have the integrals, and they're completely separate from each other. You got some data moments, and then you have some integrals of things, right? And so there it doesn't matter. You just draw a bunch of simulations to get the integrals and just have the moments. But in general, if your moment function is not separable between the data and the parameters, additively separable, say, unless you do multiplicative with 2, then if it's not separable, then yeah, you draw simulations for each observation. Yeah, generally the way it's done. Question. Anything else? Yes.
If in each step you just draw as randomly, then how would that preserve stochastic continuity?
That's actually what. Oh, okay. So let me make sure I understand your question. Drawing randomly, what do you mean when you say draw randomly?
Because yeah, I think from what, let's say for as I or m time.
Yes, you draw
So,
m times.
I'm not sure how would you draw that as n to preserve stochastic equilibrium?
Oh, okay. So that's a really, really, really good question. So the way that you preserve stochastic continuity is you have to keep the simulation draws fixed as you change theta. So you draw them once. When you change theta, you don't redraw them. That doesn't work, actually. That doesn't work. We don't know what the statistical properties of that. That's an extremely complicated thing. All of a sudden you have different simulation draws for each theta. So it makes the thing as a function of theta noisy as you change theta. Whoa, forget stochastic continuity. Right, so you draw them once and then just become part of the data. And then it's harder to do the asymptotics because that tends to pick up some discontinuities, or not pick up, but yeah, result in some discontinuities. But yeah, you draw them once. Okay, yeah, so that's really critical, actually. So, any other questions? Okay. Okay, so here's an example where you get the problem with stochastic continuity right off, because this is a kind of a toy example, but it's a good starting point anyway. Okay, so in this example, it's just binary choice, right? So we're going to think about, y 0, 1, and we have this probability, right? Y is equal to 1 is equal to h of x prime theta naught. H is, and there's our integral. H is the integral over the distribution of epsilon. So here, you can think about S as being epsilon. Okay, so you can form moment functions that look like this. Okay. And right, that's just, it's kind of, you think of that for logit, actually, you can take x times that and it's the score. For other, corresponds to maximum likelihood, it's more complicated in other settings, to get kind of the best A is a little more complicated thing, but you can think about, just some A here of x. So that's kind of your instruments, as it were, and this is your residual. Okay, and it's an integral. Okay, so we could try to, we don't need to do this, right? But we could try doing the same thing. A lot of the issues that come up with method of simulating the moment, you can see in this very simple example. So that's why we do it. Okay, so, right, you got this integral. Okay, so let's do simulation. So this is an integral over S. Okay, you can just take A of x times y minus the indicator function for S. S again is epsilon here, less than x prime theta. Okay. And so what would simulator moments be? Well, you would draw a bunch of epsilons for each I, and you would average this K over the simulation draws. All right, now because these other terms don't depend on S, they just, they in the averaging, they just come out. So that's that one. And then the second, A of x comes out too in the averaging of the part involving S. And here in the residual, you get this. So it's a sample average of an indicator function for SM less than x prime theta. Okay. So the simulated moments replace the choice probability with the average of simulated choices. It's like for each, you're calculating, it's like you're calculating, you're simulating a bunch of consumers, right? Or choice makers. And then what you're discounting the number of times that the choice one has a higher utility. Okay. That's a toy example, but you can see some things, right? Like, okay, well, that's a lot harder estimation problem. Why? Because these moment functions are discontinuous in theta. Okay, so that's the thing with multinomial choice, with binary choice here, and more generally with multinomial choice, you can easily get moment functions that are discontinuous in theta. We'll look at in a few minutes here what this looks like for multinomial choice. It's worse. Because if you're choosing over many choices, then when you draw simulation draws, you're not averaging over as many simulation draws at different cases. So it's worse that way. You need many more simulation draws. And the computation of the estimator here is challenging. You're going to do GMM here. What we're talking about now is you take these as the moment functions. They're discontinuous in theta. So you're going to try and do GMM where you're minimizing this quadratic form and functions that are discontinuous in theta. And so that's challenging to the discontinuity and the parameters of the moment functions. And it makes the asymptotic theory hard too. And that was the contribution of Bakerson Pollard. And forget that. Let's say McFadden, sorry. We do it, I mean, it's summarized and some other stuff is done in the Hamburg chapter, but really this is McFadden. Okay, anyway. Okay, so that was the contribution. This is a very nice paper, both of them, because they allow for this discontinuity in the parameters and still get root inconsistency and asymptotic normality. Using much more sophisticated stochastic technical continuity arguments than the standard asymptotic. Okay. Any questions about that example? Okay, just a couple, before we go to this pre-choice model, I'm going to just do a couple of other things about general properties and method of simulated moments. So one thing is that we already saw, right? We already saw here that identification is the same. the expectation of moment conditions is the same for all theta. So that's good to know. The other thing is, related thing, the G matrix is the same. I mean, if you think about, now it's just continuous in theta here, this example is just continuous in theta. So what you do with that is you take the expectation and then differentiate the moments to get the G matrix. The G, you'll remember, hopefully the G matrix is this, right? The G is G before, G was equal to, right, the expectation of the derivative of the moments with respect to theta. Do it here, right, and what shows up in the asymptotics is you just interchange the derivative and the expectation. Here, G is actually the derivative with respect to theta, is the expectation of the moments, so that smooths out to this continuity. Right, so that's fine, and that doesn't change, it's the same, the G here is the same. What does change is the omega, which is the variance of the moments, and there's a general, you all saw this at some point, I'm sure. If you want the variance of some random variable y, you can decompose it as the variance of the conditional expectation y given x plus the expectation of the variance of y given x. You can just apply this decomposition where think about x being the data, and so the expectation of y is the expectation of moment functions given the data, that's just g. Okay, so that gives you this leading part, which is the omega from before, and then there's another term which makes the variance bigger than for just GMM. So one characteristic of the method of simulated moments is that the variance is bigger for the simulated moments than it is for the true moments. If you GMM with the true moments, you get one variance for the estimator. If you then do simulated method of simulated moments, that increases the variance. And so that's the asymptotic variance of simulated GMM looks like this. G is the same. That's the same. The weighting matrix shows up in the same way, right? Those are all the same. But then in the middle, you have omega m, which is bigger than or equal to omega. So in other words, this, simulated moments increases the variance of having to use simulated moments increases the variance relative to GMM. Now you can, make that go away as you increase the number of simulation draws. Right? If you draw these simulation draws IID, then that'll, go away, and so you can, if you're worried about the variance from simulation, don't do 1 or 2 simulations, and do 10 or 15 or 20. Okay. All right, so how about estimating the variance? Well, you just have some moments, right? They're just moments, they're just simulated. So you just use the standard GMM formula, right? That's the standard GMM formula using the simulated moments instead of the true moments. And you just go back, right? You're just doing GMM. The only difference is your observations now have simulations in them. And you're averaging over the augmented data, the original data plus the simulation draws. This estimator works no matter how the simulations are done. The variance works no matter how the simulations are done, as long as they're independent across the eye observations. You can use sometimes, if you want to keep down the number of simulations, you can do clever things like draw an S and draw a minus, and then call minus S and use S and minus S and average them, and that tends to have a little tends to help with the variance of the final variance term in some cases. As far as estimating the variance doesn't care about that. This estimated variance, you just take the sample average of the second moments and the simulated moments, And that's consistent, no matter how the simulation draws are drawn, as long as they're independent across I. Okay. And then your estimated variance matrix is the same as for GMM, except we use this omega hat M. Now, of course, the G hat's more complicated if it's discontinuous. And that's one of the, difficulties of applying this in discrete choice is you have to worry about this discontinuity. And you say you have to, what does that mean? You mean like you have to take a numerical derivative of the moments with respect to theta. And that's a big deal sometimes, actually, in structural estimation, is trying to estimate that term. Because if you've got discontinuities and you have to meet, then you start, but that's a lot better than trying to integrate it. It's more difficult because you have to worry about taking a numerical derivative, but I think that's not too bad. I mean, they can. That's not too bad. Yeah. Okay. Questions about that? Any questions about this? Okay, all right. So this is super useful in lots of settings. I actually got, sorry, I don't know who it is, so no offense has been. But I actually got one time in second year econometrics, somebody said, what did they say on my teaching evaluation? They said, why is method of simulated moments useful? Probably because they haven't taken a kills class. Right, because you go to structural estimation, and it's immediately useful for estimating models where you have moment conditions that depend some integrals or some complicated things. So it's useful like all over the place. One of the very first structural estimation papers was this paper on patents by Pecos, and it's useful starting then, and so it's useful a lot. Okay, so I just didn't teach well enough. I could have been an example to explain why it's useful. So anyway, so this is okay. So for binary choice and for multinomial choice as well, there's a special structure. I'm going to skip this, go through this quickly. Just you add 1/n times omega. So it's one way to say it is sorry. Omega m in multinomial choice. Omega m is just one. Sorry. Sorry. If I can find this. That's is equal to omega times 1 plus 1/n, and then you can see the effect. As you increase m, that goes to 1. But that's not true in general. That's specific for multinomial choice. Okay. Another interesting thing about this, and there have actually been papers written about this a long time ago, and nobody's paid any attention, so that's fine. But simulation draws are what's called ancillary. Meaning their distribution does not depend on the parameter of interest. And at least early on in statistics, early on, 40 years ago, so it's maybe not early on in statistics, sort of in the middle of statistics, people thought about this, and an important tradition, motivated by some interesting examples, suggests that we should do inference conditional on ancillary objects. Okay, so if you have asymptotics or method of simulated moments, conditional on the simulation draws, you get bias instead of variance. Okay, and so in that asymptotics, you actually have to let the number of simulation per observation go to infinity. Okay, here you don't. And this is the beauty and the appeal as it were, of method of simulated moments is the number of simulation draws per observation is fixed. Okay, but if you treat it as biased, then M has to go to infinity just to get consistency. Current econometric practice treats simulation draws as random. So this is like a one-off. Say this once, and then forget about it. The rest of your research time. Okay. All right, any questions about method of simulated moments?
I just wanted to say one thing, sorry.
Sure, please.
In GMM, the method of simulated moments works really well because the simulation draws sort of linear in the expectation. Then if you wanted to do simulate maximum likelihood, it should be a bit more careful because then things are non-linear.
Absolutely.
Special property of GMM that you can do this.
Yes,
without changing things that much.
absolutely. Yes, absolutely. And that's really important, you know, when we talk about multi-element choice, because simulated maximum likelihood tends to work a lot better. Yeah, absolutely. Yep. So what you have to do, right? So you could, so what Nikhil was saying, so maybe I can just sketch that out. I mean, suppose what you have, let's see if I can do this. Suppose what you have is you have a likelihood function. What's true is the likelihood itself, and you can think about this as a probability, right? So suppose that you have f of w given theta is some integral of some k of, I'm going to call it something different, right? Call it some L of w, theta and s integrated over k of s. Okay, you could do that. And you could get a simulated, right? You could get a simulated value of the likelihood. You could take f hat, you know, of m w theta to be like 1 over m, some m equals 1 to m, so k of w theta sm, right? Fine. You can do that, but then let's try to find likelihood, maximum likelihood to it. What would you do? You would do 1 over m, the sum from I equals 1 to m of f log, right? Log of f of wi m. So then theta, and there's a half. And now, you know, the simulation error is not linear. I mean, this, and let me put it, that's wrong. Right way to say this is not linear in the simulation error. So what has to happen here is m, what you have to have is m goes to infinity faster than right, faster than we're doing. Required, right? And the reason for that is because you have root n theta hat minus theta, so you need root n times the simulation bias. So that's okay. So that's important because actually it's important, right? Because there's lots of models where you might want to simulate the likelihood.
People make this mistake a lot. So,
It's what?
and people make this mistake a lot. So I think that.
Right. Any questions about that? Yes.
Faster than square n means in practice, so we need like a lot more draws.
Yes. Totally. Yeah. Totally. You need a lot more draws. What have people done when they've done it right?
You could simulate before, or you can debias it. There are ways to estimate the simulation bias.
Oh, okay. Estimate, I see, device, and that gives you, it still has to go to infinity, the number of draws per observation, but at kind of a slower rate. So, yeah, so that's. So, another question? Yes.
You know why people don't like to use deterministic numerical integration for this, like the Sobel sequence or Gaussian quadration?
That's gotten a lot better, right, in the past 3 years since this was done. So I don't know what. I don't. Yeah. So it's gotten a lot better, and there are cases where people just do that. I think now. Is that
In low enough dimension, if you're 5 or lower dimensions, it's got a cursive dimensionality, but if you're in 100 dimensions, you're still probably gonna do something like Monte Carlo or something called quasi Monte Carlo or low discrepancy sequences that are deterministic points, but designed to emulate randomness, and they're good for high dimensional integration.
Also depends on how well your function is approximated by some set of polynomials. Or polynomials.
Any other questions? Yeah.
Back to the question from before, why we needed to use the same simulation, right? We cannot repro the simulations. Because in some sense, wouldn't you think that we could repro, but then the objective function, we would still find the minimum, but it would be like jiggity, so to speak.
It would be, jiggity is exactly right. That's exactly right. Yeah, chattering, yeah. And so the stochastic equicontinuity has to do with the behavior of that thing as the parameter changes. And to get asymptotics to work, you need it to be kind of smooth, approximately smooth in the parameter. And that destroys that, right? Because then all of a sudden you get, when the parameter changes, you get these jumps. And it's not smooth, approximately smooth anymore. And so, yeah, that's what stochastic equicontinuity refers to as some approximate smoothness in the parameter. Yes.
So in case of a multidimensional integral, do the dimensions need to be independent of each other when we take the draws? Something like that.
If you're clever about, not necessarily, I would, if you're clever about the simulations, not necessarily.
But for quadrature methods.
You're drawing from whatever the joint distribution is, and that's exactly. So it's whatever the joint distribution is. I mean, the way this is actually done in practice is mostly they take out the, you have to, generally they're independent. The S's that you're drawing from are independent because you take out the covariance and you put it in theta. Actually, in practice, that's what you do. So generally, they're independent. Always, I don't really know. Beyond what you know, so there's a lot more expert people in there, and I don't know that that's the way it's always done.
So I guess the wonderful thing about Monte Carlo simulation is that for its first dimensionality, it converges at root m with the number of simulation draws. That rate does not even depend on the dimension of the integral. And that's not the case for Monte Carlo. It's built in, not for quadrature, it's built in first dimensionality. Yeah.
There's one more question in the chat. What are the rules on how many simulations should be used? Simulation draws.
Well, so a simple thing is do some sensitivity analysis, right? I would try some, and then I would try maybe more than one. And if your estimate's changing a lot, then you want to, run it up. Yeah, fair enough. Yeah. All right. Okay. So let's talk about discrete choice. And in the 15 minutes we have left, we can say, I think, not very much about the whole literature, but enough to hopefully be useful to you. Okay, so discrete choice. So multinomial choice, classic problem. Each individual chooses one of J alternatives to maximize their utility. And the idea here is that, again, this represents preferences. Okay, that's a modern way of thinking about this. This is just people have different preferences about choice. And there's an unobservable component that's unobserved heterogeneity. Okay. It's not true in every case, but modern revealed preference does this. So it's. Okay, so you can use, right, you're gonna maximize, you're gonna make the choice for which has the biggest utility, which in this, this is the classic multinomial choice model, where the utility is a part that depends on observed data and parameters and a part that's unobserved, and just trying to take the sum of the two. And then you're looking at the probability of the jth choice being the probability that the jth utility is the highest. Okay, so you can write that as the probability that Vj x theta naught plus epsilon j is greater than or equal to Vk x theta naught plus epsilon k for all k. And that's an integral over the values of s, where s represents the epsilons of the product of those indicator functions for j being the max. And that's a complicated logic. That's the thing that, drove people to look at simulation estimators for these, because even with quadrature, it's difficult to do more than it used to be anyway. I don't know the current status on this, but more than 4 or 5 dimensions is extremely difficult. Okay, so you can, so you can do method of simulated moments. It turns out not to work super well in this setting unless you do some version of likelihood or some version of the score and you do some smoothing somewhere. If you just use the straight method of simulated moments here of the kind we described for binary choice, it turns out not to work super well. And, but there have been refinements over time done by McFadden and Rood and Paul Rood and others that have made it work, but it doesn't look exactly like what we just did. Okay, one important case, there's a really nice closed form. Okay, and that's multinomial logic. If these epsilon 1 through epsilon j's have what's called an independent, they're independent and they have what's called a type 1 extreme value distribution, you get a very nice form for the probability of the jth choice. It's just the exponent of the jth utility divided by the sum of the exponents of the other utilities. Okay, and this is in one form or another, this is still really important. Okay, even now, a lot of models are based on this. Okay, so it has nice numerical properties too. For yj equal to 1, say if you define a dependent variable to be the y variable to be a vector of dummy variables, j of them, each dummy variable representing one choice. The dummy variable is equal to 1 if the choice is chosen and 0 otherwise. Then the likelihood has in general, the multinomial likelihood, choice likelihood has a form that looks like this. The log likelihood is just the sum of the indicator function, right? Times the log of for that, the jth choice, times the log of the jth probability. And for multinomial logit, this is concave and the value function. And so that's a really nice feature. Makes maximum likelihood straightforward. If each of these VJs is linear in parameters, then the log likelihood is concave in parameters, and you can just get maximum likelihood. Problem is, a huge problem with this, we're thinking about this in terms of economic, as economic modeling, is that multinomial logit has this feature that if you look at the ratio of any two probabilities, they only depend on the utilities for those probabilities, right? The denominator cancels out if you take the ratio. And so you start thinking about what the implications of that are for choice models of various kinds, and they're not very good. They're not very realistic. For example, if Vj of x depends only on the price of alternative j, so you can think about you choosing among, say, anything, cars, for example, among cars, and then you certainly want your utility. You think of this Vj there as an indirect utility. It depends on the price and choosing a particular car and it depends on the price of the car. And then what that says then is that the ratio of the probability of any two cars only depends on the prices of those two cars. And that's not a very good assumption, right? I mean, if you think about luxury cars, they might be, and you think about the ratio of a utility of a, you know, what are we, BMW, right? To let's see, Hyundai, sorry, Hyundai, right? You might think that that ratio of choosing those two depends on the price of a Mercedes, right? So you might think it depends on the price of a Mercedes. So it's not a very good model for economics, okay? And so this limitation of the multinomial logit is often referred to as independence from irrelevant alternatives. Okay, IIA, abbreviated as IIA. Okay, so it's not widely used, although it does form the basis for another model that we'll get to in just a second. Any question then? Multinomial choice. Demo.
Just one comment, though. We'll be talking about the dynamic model of trading. You know, you use the car example, and even though we have logit, the IIA isn't a problem because our values are value functions that depend on all the prices in our context. So this is also partly, you know, it's a static choice context.
Okay, so specific to the static choice.
Yeah, so the problem is way less problematic in a dynamic model.
Okay, cool. Right. Any other comments, questions? Okay, so 8 minutes. It's okay, no problem, right? So mixed multinomial logit. Okay, so this has become, like, I would say, very popular, particularly in connection with Barry Levinson-Pecos and a way of doing demand estimation with market demand and individual demand where you have imperfect competition. Okay, so here, what this does is you mix over, there's some other unobserved component besides the epsilons. The epsilons are still going to be type 1 extreme value, but then there's some other unobserved component of the utility. Okay, and one way to write that, this is not standard notation, one way to write that is a vector of unobserved preference variables that's independent of epsilon 1 through epsilon j, which are still independent type 1 extreme values. Okay, here, still independent type 1 extreme values, and they're independent of SJ. And then you put this unobserved thing in that part of the utility. Okay, now what that does for you is you can condition on the SJ and do the integration over the epsilons, okay, to get a nice closed form for the conditional probability of x equals 1 given x and SJ, and then you can integrate over the SJs. Okay, and this has, you know, really pretty good numerical properties. And what's happened is you kind of integrated out the indicator functions for the choice by first doing the integration over the type 1 extreme values, and you get these for the probabilities. Okay, and so simulation straightforward, right? You would just, and furthermore, it's nice and smooth in the parameters. You would just, you've integrated out the epsilons, and so then you just draw simulation draws for the S's, right? And you just, there's your simulated probabilities right there. They're nice and smooth in theta. You can do maximum likelihood, no problem. This was done a lot in practice, in particular in connection with Barry Levinson-Pecos and estimating the demand model for imperfect competition. Okay. Okay, it does break IIA. How much this frees up cross price effects is a matter of some debate. Yeah. That's okay. It's a matter of some debate. Okay. Anyway, never mind. Go on. Okay, so there's the choice probability. Anyway, I'm sorry. Choice probability is there, and you know, again, it's a nice Okay, one thing I want to say about this is, remember, this S has a known distribution. So one way to think about this is S perhaps is normals. You could think about a model, simply S as normals. You could think about a model where, you take, it's linear in some betas, okay, but you have a mean value of the beta. And then you have, these are standard Gaussian, the S's, they're all standard normals. And then you have some matrix, which is basically the square root of the variance matrix. That's like say a lower triangular matrix. And then what this gives is a distribution for the coefficients. So this is a heterogeneous coefficient specification where you use a vector of means. So that's the average value of the parameter over individuals, and then beta is a lower triangular matrix which transforms the IID standard normals into things that have variance with each other. Most of the models that are used are much simpler than this. They're just one random parameter, the coefficient of the price variable, and very limits and pecas, but you could do it with many more. And then what you do to get the simulated probabilities is you just, again, these S's are fixed, but you take these logit probabilities and then you average them over the simulation draws, and then the parameters of this are the mean of the coefficients, right? And then the variance matrix for the epsilons. Most of the time, if you try to do this with a fully unrestricted beta vector, it wouldn't work very well because these things are not, the variances are not really super well identified here across general variance matrix for all the random coefficients. So mostly what's done is most of the B's here are 0, and maybe you have one S, the coefficient on the price variable, and you simulate that. And then all this shows is then the way you parameterize this is you have a mu, which gives the mean value of the parameter, and sigma, which is our B here, which gives the standard deviation of the parameter. And then you compute the trace probabilities in this way. Okay, so that is estimate that by you can do by multinomial choice maximum likelihood for these choice probabilities. Again, just to emphasize this, holding all the simulations fixed. Okay, no different here for mixed logit than it is for any of the other simulation things we talked about before. You draw the simulation draws once, and then what you do is you vary the mean parameter and the standard deviation parameter. Okay, so there's more on. There's more. I'm gonna pass on this one at a time. So there's more. There's a nested logit model, which is useful. One way to relax the IIA, is to nest similar alternatives. In this case, it's a choice between upscale food, Lalines and Chapany in Berkeley, right? And fast food, Bongo Burger. I've never been to Bongo Burger. Is there a Bongo Burger in Berkeley? I don't know. Anyway, whatever. There's never mind. But so this is another way to think about allowing for departures from the IIA. And if you can group products into groups, you can do this. It's a little more complicated than just mixed logit. Actually, it's a little more complicated to do this, but you can do this. There's a good reference here, and there's even more on this in Berto Avenue's notes, which will be posted along with this lecture. Okay, so you can read more. The nested logit there. Okay. Any questions about this? Yes.
Have people studied how harmless or harmful is the type 1 extreme value assumption?
I think because it's so the economics, it's not really, it doesn't really work with economics very well. I think some people are just happy to throw it out just because it doesn't really work with economics. So in the classic example, dating to McFadden's work on, I think it's motivated a lot of his work on the nested logit, is choice of transportation, straight great study done before BART was implemented, Dan McFadden did the work on, and trying to predict what the effect would be on the public transit system of putting in BART and Berkeley and use multimodal logic to do it. But then you start thinking about that. And the classic example is red bus, blue bus. Always, you look at an alternative, you want to look at a.
Oh, yeah, I guess I'm not referring to like the substitution pattern restrictions, just in general, you assume these type of shocks, like what does that mean for like underlying micro foundations of behavior?
Yeah, so it's a great question, actually. So some people, I was referring to some people who think about this issue of whether or not nested multinomial logic kind of takes care of the IA property and good enough for economics is, I'm sorry, not just nested, but also even the mixed logic thing. Has to do with whether you really want to allow these unobserved epsilons to be dependent. And that puts in completely general substitution. If you do multinomial probit and you allow a variance matrix, which can be anything for those epsilons, there's it puts in very, very general substitution patterns, actually. So it's that's a good point, actually. Yeah, people have thought about that. One paper is Hausman and Weisman, so they kind of looked at that, the problem is we just can't compute that. You're allowed to variance matrix. Anyway, there's much more on this in the literature. I recommend, Alberto's notes are good, but also if you really want to look into this, McFadden's work on the methodology is great. Thinking about the economics of it. He's got nice economic interpretations of what the utilities are and how they relate to the parameters of the methodology. Excellent.
1 hour break for lunch. That's
Much else,